Yeah, so in this video is an introduction about inner product space, and the formal definition is shown on this board. So you can take a look here. Basically, we have a real vector space here. So we have a real vector space, and an inner product space is a function that associates the real number. We use the notation, the corner brackets for each pair of vectors uv in the vector space V. And this kind of function is sending basically for any pair of vectors u and v to a real number, to a real number. So this one becomes a number. It's not a vector anymore. And such an assignment for each pair of vectors uv must follow the following four axioms. Yeah. So all the four axioms are given below. So if you just look at this page, it looks like an abstract definition, and it doesn't really provide any motivation why we have to look at the inner product space. So that's why on the next page, we'd like to look at some motivations why we're looking at an inner product space. The motivation behind the inner product is based on what we have learned in high school, the so-called dot product. So let's take a look at this example. If you're looking at the xy plane, a dot product, I believe all of you have learned this back in the maybe high school physics class. And regarding the dot product, for example, we can look at two vectors. So let's say the vector u is 1 comma 2, the vector v, let's say, is 1 comma 4. So roughly speaking, on the xy plane, we understand these two position vectors extremely well, because let's say the vector u is like this, 1 and 2. This is for vector u. And the vector v, I think it's something like this, is 1 and 4. Yeah, this is vector v. So now, and given these two vectors, we understand how to do the dot products. Do you remember how to do this one? And it's just the sum of two components, where each component is a product of the corresponding coordinates. For example, you can multiply the first coordinates for the two vectors, 1 times 1, and the second component would be the multiplication of the second coordinates, which is 2 times 4, and you have to add them up. So the answer in this case is simply 9, right? And if you have learned a bit more about the dot product, the reason why we are doing it is because, for example, I can show it below. So you see, there's a definition for magnitude of a vector. So the magnitude measure, for example, how long is this vector u? How long? Yeah, the length. You can call it the length of vector. That's the physical meaning of the term magnitude here. The magnitude of the vector by notation is, for example, if you look at the vector u is like this, and essentially we're looking at the physical length of this vector. And do you remember how to compute this magnitude of vector? This is essentially a use of Pythagoras theorem, right? So for example, if you look at this right angle triangle up there on this xy plane, and you see, if you look at this right angle triangle, the height is given by the y coordinate, which is 2. The the base length is given by an x coordinate, which is 1. So essentially, the length of the vector, we're talking about the hypotenuse of this right angle triangle. And by the basic use of Pythagoras theorem, we understand it's the same as the square root of 1 square plus 2 square, and which is square root of 5 in this case, right? So there's another way to understand the formula for the magnitude of vector. Um, it actually can be written as the square root of the dot product of u with itself. You may be curious why it is true, because you can do a quick check. So if you do the square root of the dot product with itself, essentially you're taking dot product of the vector 1 comma 2 by itself, then you'll see that it's really the same answer as what we have obtained above. Yeah. So it gives you a sense that just by the use of the dot product, we can actually use it to define the magnitude of a vector. So you can imagine it's like this. Now, once we understand the dot product, we know how to compute the length of a vector. So on the previous page, I showed you the definition of the inner product. Abstractly speaking, once you understand the inner product, which is a generalization of the dot product here, so it's like dot product is a special case of the inner product, we should be able to understand the meaning of the magnitude of a vector once we know the inner product. Yeah, so that's the issue here. So the second application that we'll look at is regarding the distance between two vectors. Yeah, by the distance between two vectors, so you can look at the previous examples. If you have a vector u, if you have another vector v, and the definition of distance between two vectors, I try to measure how long is the distance between the arrowhead of the vector v and the arrowhead of the vector u. The black one here, I want to measure how long. And I believe this one can be done because we understand that this vector that I put here, this blue vector is actually the vector v minus u, right? So it gives you a sense that the distance between the two vectors u and v is defined just by the length of the vector in blue color, which is the vector v minus vector u. So it means we can look at it in terms of the magnitude of the vector v minus vector u. Or the other way, it is the same as the magnitude of the vector u minus v. These two, when you do the calculation, they will give you the same answer 100% of the time because the fact is that the vector u minus v is the same as this. Yeah. So it's like the opposite direction of the vector v minus u. But anyway, in terms of length, the blue and the purple colors are the same. So you see this page. I just gave you two different applications of the use of the dot product because once again, whenever you compute the magnitude, we can think of the formula by the use of the square dot product because it's like the square root of the dot product. So let's come back to the big question. What are the common examples of the inner product? We have seen one case here in R2. The dot product is essentially one of the famous examples of inner product, but how about the other one? You can take a look at this case. Is it an inner product? Yes or no? And please recall there were four axioms I showed above that must be satisfied for it to be called an inner product, right? And now I claim that it is not an inner product, meaning that you have to show me at least one of the four axioms is wrong. So for example, let's look at one of the axioms. I think, for example, we can look at axiom 4. Axiom 4 means what? Axiom 4, one of the condition is if we take two vectors v by itself, it must be non-negative. If you take the inner product by itself, it must be non-negative. So, and why is it false? I claim it is false. This is the claim now. And you have to tell me why. And we can look at an example and check. For example, maybe I can look at an example like a vector like 2, 3. Now we have to compute this. We have to compute this. And let's see how to compute this. So the first vector is v, the second vector is also v. And what you need to do now is you have to look at the positions carefully. Yeah. So now, if you follow this way of working, yeah, just do this one by one. Please be careful. You see the first vector, we call it u1, u2. They are in the positions here. So 2 and 3, right? Yeah, and then the second vector is v1, v2. So please look at the positionings here. So it means I can use 2 and 3 here. Now you can do this calculation, which is minus 5, which is negative. So it gives you a sense that just by using this example, we understand that the inner product, the so-called inner product with itself now is negative. which means that it doesn't follow this rule, because this rule is saying that you take inner product with itself, it must be non-negative. And because it is now not following the axiom 4, so it means the axiom 4 is false. And it also means that it's not an inner product. Yeah. And we'll look at the second example now. So let's look at this case together. Is it a properly defined, well-defined inner product? Please look at the definition here. And I claim that it is also false, which means that you have to tell me at least one of the axiom given above is wrong. And now let's try the axiom 1. The axiom 1 is like this. When you take the inner product with itself, the two positions can be interchanged. And now I claim that it is false. And once again, to show it is false, you have to give me some examples. And for example, I'll just try my luck. I'll choose the vector u be 2, 3, the vector v be 4, 5. Let's try something. To show it is false, meaning that you have to compute the left side, and separately you have to compute the right side, and the two values are not the same. So let's try the left. When you do these calculations, now I'll follow the formula given above. So you are doing this, and for the first vector u, the u1, u2 are here. So I fill in the blank, the 2 and 3 are here. And regarding the second vector v, you see, that's the second spot here. So I think for the v is like 4, 5, right? So you can do this calculation. You will see that the answer is 31. And let's do by the right. The right side is a swap of the positioning of the two vectors v and u. Now we'll follow the same definition. Let's see whether they are the same. Let's check. So now, but please be careful. The first vector now becomes v, right? So the first vector is the 4, 5 now. And the second vector is the positions here. So the second vector is 2, 3 now. So I put it there. So you can do this calculation. Then you will see that the answer is like this, which is like this. So you see, they are not the same, right? And not the same means that in our example, the product UV is not the same as the product VU. So you give it a sense that the axiom 1 is false. And it also means that it's not an inner product. Yeah. So that's it for these two examples, which shows that they are not inner products. So it may be a good time to ask yourself, what are the typical inner product we used to see? So you can look at this page. This is a very common inner product, and some people call it weighted inner product. Some people use the term weighted inner product for this type of things. So this inner product is defined, honestly, not totally different from the dot we know, because if you look at this definition, there's a new term, which is the term d1, like d2 up to dn, but these are just some constant numbers. But these numbers must be positive. So, and I think the typical example is if you look at R2, if you look at U is U1, U2, V is V1, V2, and if let's say D1 is 1, D2 is 1, you would understand that this definition of inner product is defined by U1 V1 plus U2 V2, because now in this case the D1 D2 are 1, right? And this one is exactly the same as our dot product. So you see what I mean, right? So it means dot product comes now as a special example to this definition of inner product. Yeah. So I'm claiming that basically in this case, if you change these values, it will not be the dot product anymore, but still it will give us what we need, which is an inner product on a vector space to make it an inner product space. Yeah. So I think let's take a quick look at this page regarding application of inner product that I've mentioned earlier. So first, now we can define the norm of a vector, which is essentially what we call by magnitude of the vector based on this definition. Please recall that previously when we talk about the magnitude based on the dot product, it is defined as a formula, which is square root of the dot product with itself, right? But now we replace the dot product with the more general inner product based on our definition. And the second one, the distance between two vectors uv can be defined as the norm of the vector v minus u. Yeah, two things. So we'll look at some more problems now. So for example, we can look at this case. In all three, let's say the inner product is given as follows. Now you see this is a very typical inner product, same as the one I talked about just now. But now it's not the same as the familiar dot product because this constant d1, d2, d3 are changed to another positive number, which is not the same as 1. But now still, let's use this inner product on our R. Are you able to compute the inner product of u and v? So we can do it together. So now let's try some computation exercise. I think the answer must be like this. Yeah, and please keep the positioning in your mind. For the first vector, the coordinates appeared here. Yeah. So now for the vector u. Yeah. And let's say the vector u given is like this. Let's say the vector v given is like this. We can start the calculation now. So the vector u is like this. And the vector v, which is the second one, is like this. Yeah. So we'll fill in the blanks, you see. This is for the vector v. So it's like a 4, 5, 6. Yeah. So the vector u was already filled in based on the purple underline, you see. Yeah. So anyway, it's a computation exercise. So you can do it by calculator. So I think you'll get something like this. Yeah. So that's the first one. And let's look at the next exercise. So you see, we are still using these two examples of the vector u and v. And are you able to compute the inner product between these two vectors? Please think about this. It essentially means you have to add the two vectors first. So after addition, the vector is like this. Yeah. For the u plus v. The second vector is 2u plus v. So please do your calculation here. 2 times u plus v. Then you'll get this one plus 4, 5, 6. And the vector is like 6, 9, and 12. Yeah. So anyway, after you get these two vectors, basically you have to compute the first one. This is the first one. Which is 5, 7, 9. The second one is 6, 9, 12. Yeah. Which is 2u plus v. Now, this calculation is really the same as the part A for now. So you just have to do this one. Yeah. One by one, please. And the first spot here for components is coming from the first vectors. And the second spot, which I use the green underline now, is for the second vector, which is 6, 9, 12, 5, 7, 9. And I trust that you're able to do it by calculator yourself. It's a matter of computation now. And we can look at more examples from here. So in this case, let's try to compute the vector u regarding its norm. So please recall the vector is 1, 2, 3 for the vector u. And now let's try to do it together by the formula I showed Kate previously. The norm of the vector is the same as the square root of the inner product with itself, right? And please recall that now the inner product is changed. It is not the typical dot product anymore. We have to use the definition that I gave above. So now inside the square root, what you have to do is, but now both vectors are the same. Both are 1, 2, 3 basically. So when you do this, once again, first component, first bracket, for each term I use the purple underline. The second one I use the green one. And please do your calculation now. It's 1, 2, 3. It's 1, 2, 3. And now it is the same as this one. Yeah. So I think it's the same as square root of 47. And that's the norm of a vector u. Yeah. So we can compute it once we understand the inner product. Yeah. And the second one is, let's try to compute the distance between the two vectors u and v. And by definition, the distance between the two vectors u and v is the norm of the vector v minus u. Yeah. And please recall that I'm using the v as above, which is 4, 5, 6 in R3. So now we have to compute the vector u minus vector v minus vector u, 4, 5, 6 minus 1, 2, 3. Then you understand that the vector is 3, 3, 3. Yes, so it means that now it means you're looking at the norm of the vector 3, 3, 3, right? And you see the norm of the vector can be computed essentially the same as part C now. So it means by definition is the square root of the inner product of the vector 3, 3, 3 with itself. Yeah. And please recall that our definition of inner product is like this in this case. So I think essentially that's the first vector, that's the second vector. So you can take a look at this calculation. Yes, so I think if you do it properly, the answer to this case is 81, and which is just 9. So the distance between the two vectors u and v is the same as 9. Yeah. We can once again try another question. We can look at this standard inner product. Now, please look at the vector space. We are not looking at the familiar one like R2, R3. We are looking at the vector space of all 2 by 2 matrices. And of course, we know how to add matrix like the vector addition. We just add the matrix by matrix addition. We know how to do the scalar multiplication on the matrices. And in that case, for this vector space, the standard inner product, I call it standard because it's the most common one. And yeah, and usually we define like this. And think about the computation required on your side. You have to compute the trace of the matrix product, which is M1 transpose times M2. And let's do some calculations together. And we can try this exercise together. You can compute the inner product of M1 with M2 now. And by definition, it is the same as the trace of the matrix product of M1 transpose times M2. And please recall M1 transpose is essentially you are turning row to columns for the matrix M1. So transpose M1 is 2, 3 as the column 1 and 4, 5 as the column 2. Yeah. Now M1 transpose times M2 is like a matrix product now. M1 transpose with M2. Yeah. And please do the typical matrix multiplication row times column now. And if you do it properly, I think the answer would be minus 20 for the first spot and 22 for the second spot, and the next spot minus 26, the next one. So and then the last one will be 27. Yeah. So you should be able to get it as the matrix product of the two matrices. Now I'll put it there. We are looking at the trace of the matrix product like this, and by definition the trace is the addition of the diagonal entries. Yeah, so I think the answer is 7. Yes. So is it okay, this one? I hope it is okay. Then we'll look at the next question. We can try to next compute the norm of the vector m1. And please recall the definition of the norm of m1. It is the square root of the inner product of m1 with itself. And in the current problem, the inner product is defined inside the black box, meaning basically you have to compute the trace of the inner product of M1 with itself is the same as the matrix product M1 transpose times M1, right? So now it's a computational issue. You have to compute the matrix product M1 transpose with the matrix M1 itself. Then you'll see that the answer is as follows. So this one should be the matrix product of the two matrices. And now it means that we are looking at the trace of this matrix. And please recall the trace is the addition of the diagonals, which is 20 plus 34. So it means the answer would be square root of 54. And that's the end of this question. Let's look at the current problem now. And please look at the setup first. You are not given any actual numerical examples of the vectors. What you are given is a vector space big V and an inner product on the vector space V, and there are certain vectors u and v, such that the norm of the vector u is 3, the norm of the vector v is 2, and the inner product of u and v is minus 2. And this question you're asked to compute certain inner product between two vectors, but the numerical numbers, I mean, associated with the actual vectors u, v are not given. So we have to think about how we can get around these issues. So you have to feel comfortable with the axioms, the four axioms for the definition of inner product. So just as an example, I think you can go back to the previous video. So the axiom 2 is like if you have certain situation like this, like one of the positions, like u plus v in the first positions here, uh, consists of two vectors, linear combination of two vectors, is actually the same as this one. Yeah, the inner product of uv plus the inner product of vw. So and now if you recall the axiom 1, if you recall the axiom 1, it's like the inner product is symmetric in this sense. Inner product of uv the same as inner product of vu. This fact essentially means if that if you are having a linear combination of two vectors on the second position like this, you can actually flip it around, change position like this, right? Same thing, same thing. So it gives you a sense that you can actually look at the axiom 2 for a inner product like this, which means that this one in the blue box is the same as the sum of inner product of uv plus another inner product which is uw. I hope you get my point. I hope you get my points. So because essentially here, I'm applying the same trick as above. Yeah, it's really the same trick. So I'm emphasizing the fact that if either the first or the second position is a linear combination of vectors, like our current case, we can always distribute the vectors into a sum of two inner products by keeping certain positions, in this case is the W, the same, if you see what I mean. Yeah, so now, why is this rule important in solving this question? Because you can take a look this way. So let me write down the equation first. Let's focus on the first position inside the inner product. By using the axiom tool, I think I can distribute it this way, right? I'm simply using the axiom tool on the right side of this board. So, and further, please look at this. This one can be distributed kind of like this, yeah, which is essentially the axiom 2 anyway. So it means for the first bracket, what we can look at is now is a sum of two things. That's the first one, and then And similarly, for the second inner product, we do the same thing. So this for the first one, I use a big bracket to cover the both terms. I do the same thing for the second inner product now. So it's like you can do these kind of distributions, and it VU for the first inner product, and the second one is gonna be V comma minus 2V. Yeah. So I hope you see what I mean here. So and why is this important for us in this question? Because we can do further. We can go back to the axiom 3 in the definition of the inner product. The axiom 3 is saying something like this. And k is a scalar. K is a value, is a numerical value, real number. You can pull out the scalar like this. Yeah. There's a rule like this, which is embedded in the definition of inner product. So it means, for this kind of scalar, like this, like this, like this, we can always pull it out. If you see what I mean. Yes, so now it means that for the first term, it becomes this one. And the second term, both scalars can be pulled out. So actually, it becomes minus 6 now in front. And this one, we can use the axiom 1 to make it look like U inner product V plus. And once again, when you pull out the scalar, which is negative, this is. So we can just use minus 2 VV. Yeah. So I hope you get my point here. And now please take a look at all the things we have. We already know this value based on the use of the inner product of UV, which is minus 2, right? Moreover, we also know these values, which is the inner product of UV. Once again, the value is minus 2. So what we don't know are two things. This is inner product of UU and inner product of VV. So can you see how we can get it done? So now I put a note on the right side of this board. So please recall that. Now, there's some information we haven't used at all up to now. So please recall that the norm of U by the formula is the square root of the inner product of U with itself. Now it is given that it's equal to 3. So when you take the square at both sides, the inner product of U is just 3 square, which is 9, right? And similarly, for the inner product of V with itself, it is now inside the square root, and it is equal to 2 because it is some given information at the top. So it means the inner product of V with itself is 4. Yeah. So these two things are the two things we need. When we plug it back, I'm sorry, the inner product of V with itself is 4, this one is 9. So it means numerically, you can now get everything done by looking at this formula. Yeah. So definitely you can get it done by calculator. And that's the end of this question.